2.3. In fact, we got to the box on the second page. Okay, we're ready to start rolling today. So we just mentioned the definition of this word basis at the end on Friday. And I'd say basis is one of those words right up there with linear independence, span. It's one of the fundamental terms used in linear algebra. So a vector space or a vector subspace can have a basis, all right? And so what is a basis? There are two important aspects of it. So it's a set of vectors in a space where they're linearly independent and they span the subspace in question. The subspace could be the whole space. So you can get every single vector in the subspace as a linear combination of the B1 through BPs, and they also happen to be linearly independent. And so we're going to explore those two aspects of the definition. Again, I use our textbook's definition where they refer to subspace, but H could be the whole space, V, in which case we say the basis is a basis for the entire vector space. And make sure you convince yourselves that those vectors B1 through BP, the basis vectors, must actually belong to the subspace we're talking about. That's sort of obvious. Now, all right, some facts about ideas about a basis. I think we can just talk about this without me writing too much down, but this idea here in the example. If A is an invertible n by n matrix with columns A1 through AN, all right, so A is invertible. That's like the key. So A inverse exists. And A can be expressed as columns A1, A2 to AN. By the invertible matrix theorem, the columns of A have to be linearly independent. That's one of those long list of equivalences. And another item on that list of equivalences is that the A1 through AN set, they actually span Rn. So we can pull two items from that invertible matrix theorem when you have the columns of an invertible matrix. And what that implies is the columns of A form a basis for Rn. And that's any invertible A. All right, so there are lots of these bases, or basises, I'd say bases, for Rn, because there are lots of possible invertible matrices, right? So worth thinking about that idea. And then down at the bottom is a particular example. We could look at the matrix In, right, the identity matrix in n dimensions. We've already talked about how we can denote the columns E1 through En. That's a traditional notation still used. And here they are. So they form a basis for Rn, and they're called the standard basis. Let's turn the page. All right, now something a little bit more subtle, and I don't want to rush through this example because I know everybody always has trouble with it. Let n be a positive integer. Let that capital P sub n denote the vector space of polynomials of degree less than or equal to n. The claim is that these functions, these are functions 1, t squared up to tn, form a basis for Pn. it should be clear that they span Pn because any polynomial of degree n can be thought of as a linear combination of these terms. They're just the terms of different powers of the variable, right? What's the 1 doing there? Well, when you take a constant times 1, you get the constant term in the polynomial, right? And what's not so obvious is that that set is linearly independent. In other words, suppose C1 times 1, C1 times 2, all the way down the line to, I guess I end up with n plus 1, because my subscript on the c's is always 1 more than the power on t. Suppose this linear combination adds up to 0. We would have to show that that implies that the only way that can happen is for all those coefficients, c1 through cn plus 1, to be 0. And that is true. That's not obvious. We're not going to go through the details of it. It gets very technical. But you know, the only way a polynomial can end up being 0 for all values of t is if each one of its coefficients is 0. You should kind of believe that. Like if any of these coefficients were different from 0, we'd get some curvy shape, some shape, possibly even a straight line, that would not be the same as a constant 0. So what's going on here? Let's let's look at just another example. Like set n equal to 2. Then we could talk about P2, the set of polynomials of degree less than or equal to 2. We're saying it has a basis consisting of 1 t squared. Those are 3 elements of P2. Now, if you want to use set notation, you could write P2 is the set of all polynomials of the form. And I can use subscript c here. I could say c1 plus c2t plus c3t squared. To me, that's a little bit confusing because the subscripts don't quite match up with the powers of t. And this is where c1, c2, c3 are any real numbers. That's all that means. So like all possible folks that look like that, some elements of P2 might be 3t squared plus 5t minus 6, 11t plus 8, might be a constant, 7, t squared minus t plus 3. So we actually think of these guys as vectors in the P2 vector space. Just those polynomials. And we could define P3, P4. You have to have a specific n value in mind. When we write that Pn notation, we're just trying to describe all these possibilities at once. Right? Vectors in P2 also includes 1, t, and t squared all by themselves in that list. So those 3 basis vectors actually are elements of P2. Okay, is that? So we'll have homework on this. We'll come back to this type of example. It's something you got to know. It's an example of a vector space where the vectors can't be described as a column with just some numbers filled in, right? So really they're functions. In this case, they're polynomial functions. Yeah, so nobody's too excited about about this, I think. You're like, okay, what's the trouble going to be? I don't know. All right. Okay, so just some more theory before we get to a problem. I'm going to move up to the next theorem here. This is important in a box, spanning set theorem. Suppose we have a set of vectors in a vector space, and just suppose H is the span of those vectors, all right? Now, I'm not saying these are a basis, all right? I'm just saying these are a set of vectors, and a couple points. If one of the vectors in that set S is a linear combination of the others, then the set obtained by removing that vector still spans H. All right? So we know the set spans H. That's what H is. All right? We have this set of vectors. All linear combinations give us a subspace H. And we're saying if one of them, say the last one, is a linear combination of some of the others, then I can remove that last one, and what's left still spans the same set, right? I mean, if I can get VP as a linear combination of what comes before, then all the linear combinations of these guys really doesn't give me anything else, because I can already, that shouldn't be too mysterious. And you can read over A on your own if that seems a little cryptic. Part B to this is Part B is some subset of S is a basis, must be a basis for H, at least as long as H has more than one element, like H can't just be the zero vector, or we're in trouble here. So that's kind of don't worry too much about that situation. So the way to think of this is, like, suppose I have a set of vectors that span a subspace. They could be dependent. So they're not a basis yet. They're dependent. They're not linearly independent. I can find one that I remove and still have the same span by what's left over. I might have to remove another one, still have the same span. If I keep doing that process as long as I go, eventually I'm going to get down to a set that's independent. Meaning, at that point, if I try to remove one more, I'm not going to have the span being H anymore. That's the idea of this theorem. Plain English, what you guys got to know is if a set S spans a subspace H of a vector space, then we can find a basis for H inside of S, some part of S. If S is dependent, it's too much. But you can take that dependent set and whittle away, take away pieces, till you get down to an independent set that spans the subspace, and that will be a basis. Okay, that's all I'm going to say about that. We're going to flip the page so we can start heading toward an exercise. Again, the text that follows there is just a detailed explanation of my proof of part A and my proof of part B, and I'm just going to leave that to read over. We're going to go on to the exercise. So find a basis for the null space of A, where A is that matrix. We really put all the pieces in place so you can do this kind of exercise. So finding a basis means finding a linearly independent set of vectors that span the space in question. In this case, that span null A. And so for this exercise, we already, in a previous handout, we work with the same matrix, all right? We looked at this same A in, I want to say 4.2. Just make sure. Yeah. And we described null A in section 4.2. And I think we found out that null A is the span of two vectors. Remember, negative 1, 1, 0, 0, 0, and negative 1, 0, negative 1, 0, 1. How did we get those? Yeah. I mean, this was from solving AX equals 0, the homogeneous equation. And back in 4.2, I want to just write out x2 times negative 1, 1, 0, 0, 0, plus x5 times negative 1, 0, negative 1, 0, 1. That we ended up with x2 and x5 as free variables. Just reminding you what we already talked about. Now, the only thing, there's only a little bit new to this now. We know null A spans, we know these two vectors, saying this backwards, the span of these two vectors is the null space of A. In order for these two to be a basis, in fact, maybe I should say that's a claim, that the set of these two vectors form a basis for null A. That's what's new here. So, again, we already know that they span null A. That's one of the conditions for being a basis. We need to see that these two vectors are also linearly independent. And they are. Why? Yeah, I mean, it's sort of the way we found them. If you actually multiply this back out to the equations that came from the entries were negative x2 minus x5, x2 minus x5, 0, x5, right? The only way a linear combination of these two could be equal to the 0 vector is if all entries of this vector are 0. But because of the presence of the free variables, When we have a free variable, you're always going to have entries that are just the free variable. Okay? And again, I don't want to write out this whole explanation. I just want you to see if this is equal to 0, 0, 0, 0, 0, so suppose a linear combination of these two vectors is equal to 0, that implies that x2 is equal to 0 and x5 is equal to 0, because this entry will be 0, this entry will be 0. So the only way for a linear combination of these two to add up to 0 is for both x2 and x5 to be 0. That's exactly what it means for those two vectors to be linearly independent. So I'm just going to say check without writing out a long explanation. I'm going to give you something in a moment, too, that verifies this. So done. We have our basis. In fact, our process for finding vectors that span the null space produces a linearly independent set. So our process for solving the homogeneous equation is always going to give us a linearly independent set of vectors. So just make a note on our, on our next exam, you're going to be asked to find a basis for a null space of a matrix, this type of question, right? Now, find a basis for column space of A. This is a different matrix, all right? In this case, A is just this 2 by 2 matrix, 2, 10, 3, 15. Finding a basis for column space of A is trickier. Because when you go through row operations, that actually changes the space spanned by the columns of the matrix. And I wrote out the example here right on the handout. So the previous one, I didn't write it all out because we've basically done that already. We just can use our answer from 4.2. Here, though, let's see. Column space of A means the span of those two columns. Those are the columns of A. And just notice, in this example, 10, 15 is a scalar multiple of 2, 3. So those two columns are not linearly independent, right? That's a dependent set. So I actually could express this in a simpler way. I could just look at the span of 2, 3. That already includes the vector 10, 15, right? And so the single vector 2, 3 is a basis for the column space of that matrix, okay? Am I off in my own world? Just again, there are two columns. Officially, the column space is the span of these guys, two vectors, but they're not independent. It's easy to show one depends, one's a scalar multiple of the other, so we can remove 10, 15 from that spanning set. What's left is just 2, 3. Its span will still be the column space of A, right? Because all linear combinations of these two can be obtained just by taking scalar multiples of 2, 3. Okay? And a single non-zero vector is linearly independent, so we can actually say that single vector is a basis for the column space. So simple situation because we have one non-zero vector. But if we apply row operations to that matrix, so say we row reduce, it gets down to this matrix, 1, 5, 0, 0. So call this matrix B the row reduced form. We get a matrix with these two columns, okay? 1, 0, and 5, 0, as seen there. They're not linearly independent again. Again, I can just express the span using just one of those two vectors. And actually, you should be able to see the span of this vector 1, 0 is very different from the span of 2, 3, right? The span of 2, 3 just means scalar multiples of 2, 3. The span of 1, 0 is just scalar multiples of 1, 0. All the second entries will be 0. So the moral of the story is the column space of A and the column space of B, the row reduced form, are not the same space. All right? When you row reduce, you get a different space. But, and a basis for the column space of B is not a basis for the column space of A. So we can't just use the row reduced form. And however, what we can do and what we are going to do is here at the bottom of this sheet. If A and B are row equivalent, the set of column vectors of A are linearly independent if and only if the corresponding set of column vectors of B are linearly independent. A set of column vectors of A forms a basis for the column space of A if and only if the corresponding columns of B form a basis for B. So we're going to do an example here in a second because we got to. But just going back to this example, here's what we may end up doing, or what we will end up doing. Say we want to find a basis for the column space of this matrix. We are going to row reduce. And in row reduced form, it will be easy to see that 1, 0 all by itself, this is actually a basis for the column space of B. All right? That's not our answer for the column space of A. All we got to do is go back to 1, 0. 1, 0 was the first column of the reduced form. Back up to the first column of the original matrix A. That vector will be our basis vector, in this case 1 vector, for the column space of A. And normally we'll end up with more than one, but let's go through an example and do some calculation here. All right. So, dun, 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 dun. Yeah.
Why can't you arbitrarily choose just 5, 0 instead of 1, 0 as the basis for?
Oh yeah, it doesn't matter.
Okay.
Doesn't matter which one. You just have to pick one. So there's no rule. When we have a dependent set, there's no rule like this is the vector you get rid of and this is the one you keep. Different people could possibly get rid of different vectors. All right. I think when we go through an example, this will be pretty clear. Let me try to straighten it out. So this is, again, box. So what you guys got to know is to find a basis for the column space of A, row reduce A to echelon form B. The pivot columns form a basis for the column space of B. The corresponding columns of A form a basis for the column space of A. All right? And let's do, so we got to do some calculation. Too much talk here without doing a problem. So just to kind of situate us right now, there are these two spaces, null space, column space. Finding a basis of the null space, what I was throwing my hands around about was I'm saying we already know how to do that from 4.2. We were finding a basis. We just weren't calling it a basis yet. Finding a basis for the column space, this is something new that we're going to go through. And so, let's do the exercise here. Find a basis for the space spanned by these vectors. And so that exercise is the same as finding a basis for column space of A if we say that A is a matrix with those columns. So I'm just playing around with the vocabulary here a little bit. All right, it even has the 0 vector in it. Notice that this is already in echelon form. And we have 2 pivot columns, right? Now, I think so our basis for column A is just going to be those 2 pivot columns, 1, 0, 0, 0, and 2, 1, 0, 0. That's it. So we're just looking for the pivot columns. Now, why does it just come down to that? Can you believe that these 2 columns will span the column space of A? Or another way to think of it is, can I get the other columns as a linear combination of these 2? And actually, you certainly can get 0. We can also get the last column as a linear combination of these 2. I can take 2 times the second one, and then I can just adjust the coefficient of the first to make sure, because I can adjust the coefficient on this first entry to make sure I get -1 from the first. And so they actually, the pivot columns are going to span the column space. And are they linearly independent? That is not totally obvious, but I have that written up on a separate handout that I'm going to give you in a minute. All right, I want to just go through the process first. So that's A. A is the more straightforward one. B, find a basis for the space spanned by, or the second exercise, find a basis for the space spanned by 1, 2, 6, 2, 7, 6, 4, 11, 8. So again, let our matrix have those columns, 1, 2, 6, 2, 7, 6, right? 4, 11, 18. We want to find a basis for column space of A. So the problem's worded in a slightly different way, but we just turn it into this statement, which is equivalent. Okay. Now this matrix is not in echelon form, so we are gonna row reduce. 1, 2, 6, 2, 7, 6, 4, 11, 18. And I'm not going to write out all the steps, so there are some steps here. And what I got was 1, 0, 0, 2, 1, 0, 4, 1, 0. Okay. So in my row reduced form now, I have a pivot column in the first column, I have a pivot column in the second column. Third column is not a pivot column. So these are the pivot columns. So what's my basis for the column space of A is, here's just the moral of the story. For the row reduced form, the pivot columns form a basis for its column space. But if we want a basis for A, we're going to go back to the corresponding columns in the A matrix. So I'm just going to take the first one, 1, 2, 6, and the second one, 2, 7, 6, but not the third, right? And that's my answer. If these two vectors are linearly independent, these two columns must be linearly independent also. Again, if these two span the column space of the row-reduced matrix, these two columns from the original matrix must span the column space of that matrix. Does it just seem like I'm doing magic tricks? I don't know. No? All right, so I got something else for you for today. I wanted to separate out like what you got to be able to do from some more of this discussion of the ideas. So this is another one of these optional sheets that you can ignore if you want. So what you got to know how to do is find a basis for a null space, find a basis for a column space. So we kind of outlined the process just now without, and I totally admit I was not filling in all the details of the argument. Okay. And I just want to go back to these questions. And again, the actually details of this handout you don't have to know. But I just want you to see that to me, these are the questions that came up along the way. So question 1 was, when we identify a spanning set for null A, how do we know that we have a basis? Again, basis means they're independent and their span is the space we want. We know their span is the space we want because of the way we find the general solution to the homogeneous equation. So really the only part of that question that was kind of hanging was, how do we know the vectors in the spanning set are linearly independent? So I just wrote it up here again, where I go back to that same example we looked at in both just now a few minutes ago and also back in 4.2. Really, it just comes down to the fact that because x2 and x5 are free variables, the only way we can get a zero vector will be if both x2 and x5 are equal to 0. That's exactly a statement of what it means for two vectors to be linearly independent. So, boom. So, moral is every free variable will always correspond to a vector in the spanning set, and these vectors will always be linearly independent. That was question 1. Question 2, how do we know the pivot columns in A form a basis for column A? So back in this example, how did we know those two pivot columns both span the column space and are linearly independent? And it gets a little deeper. And I'm not just going to, don't worry, you don't have to get through all these details, but I break it down into, if you look at the reduced form of the matrix A, first you can show that the pivot columns of B are linearly independent and the non-pivot columns are contained in the span of the pivot columns of B. this actually is a reduced form, so that lemma applies to the argument here. Showing that those two columns are independent and also that they span the column space. I'm not going to talk through the reasoning there. I'm just going to leave that for you. The second helping theorem is if A and B are two row equivalent matrices, then any linear dependence relationship involving some or all of the columns of B also holds for the columns of A. So we could look at this example. Any linear dependence or independence relationship between these columns matches up with a linear independence or dependence relationship of the columns of the original matrix A, even though the actual column spaces are different. And that's all I'm going to say, because that's details. And that leads up to theorem 6 from 4.3. The pivot columns of an m by n matrix form a basis for the column space of A. And I'm not going to go through the details of this proof. I'm just going to leave it here on this handout. All right. And there's one more question that's raised. This actually came up last semester because there are some of these technical details that we kind of brush over. And so I wrote something up about this. And it's worth just addressing this question, I think, now for us all. Like, is a basis of a vector space or subspace the largest possible set of linearly independent vectors just in that space? And the answer is yes. It should seem like it should be. So once you have a basis, say you have n vectors, or say you have 3 vectors that are a basis for a space, is there any way to find a basis that has 4 vectors? Or let's just look at this example. Here are 2 vectors that are a basis for the column space. Is there any basis of the column space that could have 3 vectors or more vectors? And the answer is no. In fact, every basis will have exactly 2 vectors. We see that a couple sections down the line, but we kind of want to use this fact now, even though in our textbook it doesn't come up for a couple sections due to technical reasons. So for those of you who are concerned about the theory, again, the answer is yes. And you can write out a proof of this statement. So suppose H is a span of 3 linearly independent vectors, b1, b2, b3. Could you have a set that has of linearly independent vectors that has more than 3? And in this little argument I make, I say, suppose there were 4 vectors, totally different vectors, that are linearly independent and has the same span. You can actually show that's impossible. All right. And you don't, again, have to read through it, but it just came down to writing out a whole bunch of equations with a whole bunch of coefficients, and it ends at the end of that last page. So that's it. That's all we're going to say. We're going to move on to 4.4. So the kind of the goal of what we just did was 2 things you guys got to know how to do. Find a basis for the null space of a matrix and find a basis for the column space of a matrix. All right, and now we're going to talk about 4.4. So this next section, 4.4, that we're just going to enter into briefly for a few minutes here is got a lot of ugly notation attached to it. This is an area that people usually aren't too crazy about. So we'll try to try to simplify the notation as best I can to make this understandable. So Theorem 7 from our chapter. Now we're using curly B to represent a basis, right? So suppose curly B, B1 through Bn, is a basis for a vector space. Let X be any element of the vector space. Then there exist unique scalars C1, C2 through Cn such that X is a linear combination of those basis vectors in this